Today's topic is types of magnetic material. So, classification of magnetic material based on this permanent dipole. Permanent dipole means if a magnet has a north pole and a south pole, one pole is north and the other one is south. So, two poles are there. That is called dipole. So, based on the permanency of this dipole, we can classify magnetic materials into two categories: the magnetic materials with no permanent dipole and magnetic materials with permanent dipoles. If the magnetic material has not a permanent dipole, then it is called diamagnetic materials. If it has permanent dipole, it may be para, ferro, antiferro or ferrimagnetic materials. Then the classification of this para, ferro, antiferro and ferrimagnetic material. Then first we observe the permanency of dipole. Then we consider the alignment of dipole. If the alignment is random arrangement of dipoles, then it is paramagnetic materials. Uniform arrangement of dipole, then it may be ferro, antiferro or ferrimagnetic material. Then we have to locate whether the material is ferro, antiferro or ferri material. For this we consider the direction of dipole. So based on the direction of dipole, if the dipole is along the same direction, then the magnetic material is ferromagnetic material. If the direction of dipole is opposite direction, then the material is antiferro or ferrimagnetic. Then we have to classify antiferro and ferrimagnetic material. So to classify this, consider the magnitude of dipole. So based on the magnitude of dipole, we can classify it into antiferro and ferrimagnet. If the magnitude of dipole is same, then it is antiferro. If the magnitude is different, then it is ferrimagnetic material. So the main classification is based on the permanency of dipole. We can classify it into two: diamagnetic material which has no permanent dipoles. Para, ferro, antiferro, ferrimagnetic material has the dipole moment, have the permanent dipole moment. Then we have to group para, ferro, antiferro and ferri. First we consider the alignment of dipole. If the dipole is randomly arranged, paramagnetic; uniformly arranged, ferro, ferri or antiferro. Then consider the direction of dipole: uniform direction, ferromagnetic; opposite direction, antiferro or ferri. Then consider the magnitude of dipole: if they are in the same direction, antiferro; different direction, ferrimagnetic. Then we go to the detailed classification. First one is diamagnetism. The properties are: no permanent dipoles are present, so net magnetic moment is zero. What is the meaning of net magnetic moment or induced magnetic moment is zero? If we place a magnetic material, diamagnetic material in a magnetic field, no given magnetic field lines enters into the body. That means induced magnetic field in that case is zero. That is represented as no permanent dipoles. The number of orientation of electronic orbits is such that the vector sum of magnetic moment is zero. Vector sum of magnetic moment is zero means here no such external magnetic field lines enters into the body, and the external field will cause the rotation of action on the individual electronic orbits. Dipoles are induced in the material in the presence of external magnetic field. That is the important thing. So when a diamagnetic material is placed in a magnetic field, diamagnetic material is placed in a magnetic field, what happens? A new magnetic field is developed or new magnetic field is induced, and that magnetic field has no relation with the applied magnetic field because that induced magnetic field is not due to the external magnetic field. External magnetic field means no external field lines enters into the body and leaves out. But when a diamagnetic material is placed in a magnetic field, no field lines enters, but a new magnetic field is developed. So we can observe the magnetic domains and magnetic field of diamagnetic materials. So here in this diagram, when no applied magnetic field is developed, no domains are there. But when applied magnetic field is field is applied, the applied magnetic field is along this direction. This arrow mark represents the direction of applied magnetic field, and here magnetic domains are in the opposite direction. That means the induced magnetic field is against the direction of this applied magnetic field. Then the magnetic field, here we can see that a bending of this magnetic field lines. Bending means this magnetic field lines are expelling from the body or repelling from the body. This magnetic lines repel means due to the presence of a new magnetic field, this magnetic field lines repel. These are in the opposite direction. A new field is developed which is in the opposite direction. So due to the presence of this opposing magnetic field, the given magnetic field lines are repelling. Then diamagnetism, the external magnetic field produces induced magnetic moment which is due to orbital magnetic moment. Induced magnetic moment is always opposite to the direction of applied magnetic field. So magnetic induction in the specimen decreases. Magnetic susceptibility is small and negative. Ripple magnetic lines of force. Diamagnetic susceptibility is independent of temperature and applied magnetic field strength. Then susceptibility is of the order of 10 raised to 5. Relative permeability is less than 1. It is present in all materials, but since it is so weak, it can be observed only when other types of magnetisms are totally absent. Examples: superconducting elements in superconducting state, then zinc, gold, these are all diamagnetic materials. Then goes to paramagnetism. The properties of paramagnetic material is, if the orbitals are not completely filled or spin not balanced, in overall small magnetic moment may exist. That is, paramagnetism is because of orbital and spin magnetic moment of the electron. Possess permanent dipoles. In the absence of external magnetic field, all dipoles are randomly oriented, so net magnetic moment is 0. This is random orientation of magnetic dipoles. Then spin alignment is random. The magnetic dipoles do not interact. So we can observe the paramagnetism, magnetic domains and magnetic field of paramagnetic material. When no field is given, no applied magnetic field, that means H is equal to 0, a random arrangement of domains are there. When a magnetic field is applied, all the magnetic domains are along the direction of the applied magnetic field. Then when a paramagnetic material is placed in a magnetic field, the given magnetic field line enters into the body and leaves out. So in the presence of magnetic field, the material gets feebly magnetized. That is, the material allows few magnetic lines of force to pass through it. A relative permeability is greater than 1. The orientation of magnetic dipole depends on the temperature and applied field. Susceptibility is independent of applied magnetic field and depends on the temperature. Chi is equal to C by T, where C is the Curie's temperature or Curie constant. Then paramagnetism, with increase in temperature, susceptibility decreases. Susceptibility is small and positive. These materials are used in lasers. Paramagnetic property of oxygen is used in NMR technique. The susceptibility range is 10 raised to minus 5 to 10 raised to minus 2. Examples: alkali metals, transition metals, etc. Then ferromagnetism. So ferromagnetism, origin of magnetism in the form in ferromagnetic materials are due to spin magnetic moment. So permanent dipoles are present, so possess net magnetic moment. Material shows magnetic properties even in the absence of external magnetic field. Possess spontaneous magnetization, that means immediately they get magnetized. Spontaneous magnetization is because of interaction between dipoles called exchange coupling. So we can go through the ferromagnetism, magnetic domains and magnetic field. So here, in the absence of external magnetic field, the domains are aligned. In the presence of applied magnetic field, all the domains are along the direction of the applied magnetic field. Then when we place a ferromagnetic material in a magnetic field, all magnetic lines enters into the body and leaves out. So from this diagram we can say that even in the absence of magnetic field, the domains are aligned. That means in the absence of magnetic field, a magnetic field is there. When placed in external magnetic field, it strongly attracts lines of force. All spins are aligned parallel and in same direction. Susceptibility is large and positive. It is given by Curie-Weiss law. That is, chi is equal to C by T minus theta, where C is the Curie's constant and theta is the Curie's temperature. When temperature is greater than Curie's temperature, then the material gets converted into paramagnetic. They possess the property of hysteresis. It will be explained. Then material gets divided into small regions called domains. Example: iron, cobalt, nickel, etc. So in ferromagnetic material, even H is equal to 0, the dipoles tend to strongly align over small particles. That is the diagram. When H is applied, the domains align to produce a large net magnetization. Large amount of induced magnetic field is there. Then Curie's temperature. Curie's temperature is the particular temperature at which a ferromagnetic material becomes paramagnetic. That means the ferromagnetic material changes to a paramagnetic material. Below the Curie temperature, the ferromagnetic are ordered and above it is disordered. So the saturation of magnetization goes to 0 at Curie temperature. So Curie temperature is an important point. It is the particular temperature at which a ferromagnetic material becomes a paramagnetic material. Then hysteresis curve. The meaning of hysteresis is lagging or retarding of an effect behind the cause of the effect. So for every effect there is a cause. Cause and effect relation is there. So here the effect is induced magnetic field. This effect or magnetic field induced is due to the presence of an external magnetic field H. So here the effect is B and cause of the effect is H, also called BH curve. That is the hysteresis curve in the case of magnetism. So hysteresis is magnetic material means lagging of magnetic induction or magnetization behind the external magnetic field H. That is called the hysteresis curve. The hysteresis curve is given here. Along the x-axis we take the magnetic field H. Along the y-axis we take induced magnetic field B. So here we can see that. So this is the saturation point. From when the saturation point is reached, then this magnetic field get reduced. Then in the negative direction also a saturation point is there. When saturation point is reached, this magnetic field get reduced. That is hysteresis curve. Thank you.